So yes, indeed, Terry basically stole the punchline. That is one of the amazing things to consider, is that when you do look up at the night sky, essentially every star up there we think has at least one planet around it, which is something which is incredible, given that 15 years or so ago we had no proof of any planet outside of the solar system. So what I want to do tonight is to bring you up a little bit up to date, tell you exactly what's happened in the last 15, 17 years or so, give you a little bit of the history. It's kind of tortuous, it's kind of an up and down history. But I'll bring you up to date, show you some of the latest discoveries, and also talk a little bit about what the implications are for finding habitable planets in the future, the ideas that NASA has lined up for us, if we can ever find the money to pay for them at least. Okay, so here we are, 2013. If you go back to 1995, here's what was on the cover of Time magazine. This is when the era, this new era of the discovery of planets outside of the solar system first began. 15, 17 odd years is not much in the history of astronomy. Galileo is finding the moons of Saturn 400 odd years ago. It's unfortunately only recording for the video camera. I'm not sure if I can speak much louder because I'm talking all day. Do you have a microphone that's a public address system microphone? I certainly want people to be able to hear me. That sort of defeats the purpose otherwise of my being here. I mean, the slides are great, but hopefully I add something to it. I see. Well, let me go on with the talk, and I'll try and speak a little bit louder and see how long my voice holds out. So in 1995, that's not that very long ago in the time scale of history of humanity, although if you look at that political banner in the upper left, it seems like it was quite a long time ago. The young people in the room may think that refers to Liddy Doyle and Hillary Clinton, but it doesn't. So a lot of things have happened since then, but this is basically history that's developments in science that have happened in your lifetimes, the most recent lifetimes of everyone in the room. I don't think anyone here is younger than 18 years old or so, well, maybe a few children here, but for everyone else, this happened while you were around and reading the newspapers. But you might wonder, why did it take so long? Why did we have to wait until 1995? People have been looking for planets for close to 100 years now. And you might say, well, why didn't the Hubble Space Telescope just go out and take a picture of one of them? And here's the reason why. It's summarized in this plot, which shows the amount of light given off as a function of wavelength by a couple of representative planets compared to the sun's light. So these are visible wavelengths where the sun gives off most of its light, and the Earth and Jupiter both shine at those wavelengths by just reflecting sunlight, so they have the same spectrum as the sun spectrum in this idealized sense, but they're about 1 billion to 10 billion times fainter. That's the problem. It's not that the planets are that faint. These planets, if you looked at them in reflected light, are no fainter than a very faint galaxy of the sort that the Hubble could take a picture of. Like in the Hubble Deep Field, they stared at galaxies that were very distant, that were just as bright as these objects. But the reason Hubble could see those galaxies was there wasn't a bright star right next to them. Right? They looked in a region of the sky where there are no stars, so they could stare for hours at a time and see something very faint. Problem here is you're looking for something faint right next to a spotlight pointed right at your eye. So it's a contrast problem, not a photon limited problem. But you'll notice if you go out to longer wavelengths, infrared wavelengths, the planets give off their own heat, thermal emission, depending on the warmth of the body. And that narrows the gap a bit. The sun's spectrum is still dropping off. But in addition to the reflected light, you get light emitted by the planet itself. And then your gap is no longer 1 billion or 10 billion to 1, it's more like 1 million to 1. So things look more promising, in some sense, to infrared wavelengths. And I'll show you some of that at the end of the talk. But it's still challenging, because also for infrared wavelengths, in order to resolve things, you have to have a telescope. If you're at 10 times longer wavelength, the telescope has to be 10 times larger to have the same resolving power. So there's trade-offs there too. But that's why the wonderful Hubble Space Telescope, which we come to think of as having done everything in astronomy for the last 20 years, cannot do this. It's done some important stuff, but it can't really go out and take a picture of a planet. So most of the planets found so far, at least until the Kepler mission was launched, which I'll tell you about later on, were found by ground-based observations which do not find the planet directly. They find the planet indirectly. And the way they find the planet is by noticing that the stars are doing something very odd. That's based on the fact that something we all learned in elementary school is incorrect. The planets do not orbit around the sun. The planets and the sun both orbit around the center of mass of the solar systems. Center of mass. And so here's a very simple diagram. Supposing you have a planet which is 1/4 as massive as the star, the planet will go around an orbit which is 4 times larger than the star's orbit around the center of mass of the system. It's just like the balance point on a teeter-totter. In the case of our Jupiter around the sun, Jupiter is 1,000 times less massive than the sun, and it makes the sun wobble back and forth over 12 years, which is Jupiter's orbital period. If we were looking at the sun from nearby star, we would see the sun, for no odd reason, wobble, as it was moving across the sky, wobble back and forth every 12 years over a distance equal to the sun's diameter. You know, we can all see the sun in the sky that looks pretty big to us, but if you were on a nearby star, you can't actually see the diameter of a star very easily. So it's actually equal to an angle on the sky of a 1 milliarc second, 1,000th of an arc second. That again, just to give you a feeling for what that is in size, that's the angle subtended by a dime at 1,000 miles. So that's pretty tough. And if you want to find an Earth, and an Earth-like orbit around a nearby star, the signal, the wobble is still there again. On top of the big wobble due to Jupiter, there'd be another little, with a 12-year period, there'd be a 1-year period due to Earth. But that wobble is 1,000 times smaller yet. That's basically 1 microarc second. So there are plans to build space telescopes that could observe that, which I'll show you towards the end of the talk, but it's a very challenging thing to do. So the folks who started trying to use this classical technique of trying to find planets indirectly by watching stars wobble as they move across the sky, the fellow who really gets most of the credit for starting the field is a Dutchman by the name of Peter van de Kamp. In 1937, he became the director of the Sproul Observatory at Swarthmore College. And he, next year, 1938, he put on his program of looking for stars that were trying to get binary star orbits primarily. He added a star called Barnard's Star. Barnard's Star had been discovered in 1916 by Edward Emerson Barnard, who was an amateur who became good enough at finding comets, so he became a full-time astronomer. And the neat thing about Barnard's Star is it's essentially the second closest star to our solar system. The only closer system is the Alpha Centaurus triple system. That's at about 4 light years away. Barnard's Star is about 6 light years away, still pretty close by. And unfortunately, it's not a star you can see by eye. It's low enough in mass. It's a so-called M dwarf with a mass about 1/7 the mass of the sun, so it's not a visible eye object. But the neat thing about it is it's screaming across the sky at what's called 10 arc seconds per year. It's I think the fastest motion non-solar system object. And that's because it's so close by. You can think of an airplane flying at a distance. It doesn't seem to be moving very fast, but if you see an airplane real close to you, it zooms right across the sky. Same thing with Barnard's Star. It's moving real fast because it's close by. So that's how it was identified as a likely close star through its high proper motion across the sky, as it's called. And the great thing about close by stars is that means that wobble you're looking for is that much easier to see. If you're 10 times closer, the wobble looks 10 times bigger. So you want to look at nearby stars. Barnard's Star is perfect for that, second closest star system. And it's also low mass. It's 1/7 the mass of the sun. That means if you're out there on the edge of the teeter-totter, you can make that star go up and down 7 times larger than you could a sun because it's 7 times lighter. So everything works in the direction of saying, wow, Barnard's Star is a great one. If it has a planet, it should be wobbling. So Peter van de Kamp put it on the observing program in 1938. Many generations of undergraduates spent hours late at night on the 24-inch Sproul refractor, taking plates of Barnard's Star over and over again to try to compare the location where the star is compared to background stars to see if they could see it wobble with time. He took 2,400 plates, old glass plates, photographic emulsions, and waited until 1962, or in this case 63 for this paper, before he published the claim that he actually had found a planet around Barnard's Star. So what's being plotted here is the apparent motion of that star in a fixed reference frame in 2 coordinates, what astronomers call right ascension and declination. It's just basically X and Y on the sky, showing that it seems to be wobbling with a period of about 24 years. He had 25 years of data. These data points are reproduced again. So these are the same data points as these, just to show you that it should be periodic if you followed it far enough in time. He's trying to measure the location of the star on these rather grainy aluminum colloid emulsion plates to within 1 micron. And the amplitude of this wobble was basically at 10 milliarc seconds. So it's about 10 times the amplitude of what you would expect for a Jupiter or so at 10 parsecs, because this star is closer, so it's a bigger amplitude. And the line that's here is what the wobble would be if you had a planet with a mass of 60% larger than Jupiter, 1.6 Jupiter masses, and if it was orbiting at 4.4 times your sun distance instead of 5.2, called the AU. So it's at 4.4 AU instead of 5.2 AU. That sounds normal, sounds sort of like what you might expect. The only odd thing about it is that the orbit has a little, it's not quite a sinusoid. You see it's got a little bit of a cusp to it, and that means it's a little bit eccentric. But hey, it's the only other planet we know of outside our solar system, why not? This one went into the textbooks. Everyone said, yeah, we expected them to be there, they're there, problem solved. What else can we do? What else is interesting in astronomy? Well, unfortunately for Van de Kamp, other people thought, I wonder if that's really there. And so about 10 years later, along came this fellow, George Gatewood. He was a graduate student at the University of Pittsburgh's Allegheny Observatory, and he was going to do some sort of thesis project on astrometry, the old classical science of measuring the positions of stars on the sky. It sort of predates astrophysics when people began worrying about spectra. This is a very classical technique. And one of his professors said, George, I think you should go back and look at Barnard's star and see if that's real or not. And George says, no, I don't want to get into that one. And then next time he went back to the professor says, George, I think you should think about working on Barnard's star. And at that point, George began thinking maybe he should work on Barnard's star. Because your thesis advisor kind of rules your life. And so he decided to work on Barnard's star, but he went in a completely different direction from using the original plate material that Van de Kamp had been generating with the Sproul 24-inch refractor. Instead, he had a whole new set of plates that the Allegheny Observatory had taken, as well as some from the Van Vleck Observatory. He only had 240 plates, though. He had 10 times fewer plates than what Van de Kamp was using, but he had one advantage, which was that by 1973, they had just installed a new plate measuring machine at the U.S. Naval Observatory in Washington, D.C. And so rather than have to have people sit down with a microscope and try to look at this grainy emulsion and try to figure out exactly where the center of that blurry blob is within a micron, they put it into a machine and let the machine go through and scan the plates. And if it made an error, at least it made the same error over and over again. Whereas with human beings, you can make an error, but it may be a different error tomorrow, same person, just depending on if you had too much coffee that night or whatever, right? So you take out the human element, let a machine do it, and he also did the work in concert with Heinrich Eichhorn, who was involved in this thesis. And this was actually happening close by here. This was happening over in Tampa at the University of South Florida, where Eichhorn had moved as a professor, and Gatewood was there. And by chance, I happened to be there too. I knew these guys were walking around campus. I had no idea what they were doing. I was in physics, never took an astronomy class in my life. They were doing this stuff. And I got to become good friends with George Gatewood later on in life, but we were like two ships passing in the night. He was doing this important work, and I was doing physics at the time. So yeah, that's a good slip, isn't it? Yeah. Physicists in the audience, that didn't happen. Okay. I've got 3 degrees in physics, so I've got no one to complain about myself. Okay, so they worked on this in 73, and then they published their paper as well. So here's their paper, 73, and they're just plotting 1 coordinate here on the sky, not 2 coordinates. And the size of the data of the plot here tells you something about how much belief they put in that particular data point. So these big black ones they like a lot. These here, as they got smaller and smaller, they don't quite believe so much. And this one here is a speck of dust that was on the slide that I used to make the PowerPoint presentation. So I think Peter Van de Kamp probably would have liked to keep that dust plot there, but that's not real. So ignore that one. So the point was, even though some points seemed to fit what was the predicted orbit, the other ones, and especially the big ones, which are again repeated here, those 2 are the same as there, they really don't fit. They're within the noise that they have in the measurements. There's no support there for Van de Kamp's orbit. So Gatewood and Eichhorn were very gentlemanly about that. They simply said in their paper, they didn't do a big press release or something, they simply said, we can find no evidence for the planet around Barnard's star, and let it lie like that. But things got even worse for Barnard star's planet in that same year, because one of Van de Kamp's colleagues at the Sproul Observatory, John Hershey, published his own paper in the same year on another star that they'd been following at Sproul called GJ793, which also is a low-mass M-dwarf star. And the odd thing was that if they looked at the motions of Barnard's star and GJ793 as a function of time, they both kind of wobbled up one way and wobbled down the other way and wobbled up the same way, as if they both had exactly the same planet at the same phase or the orbit, which seems a little unlikely, or else they were wobbling because the images were taken with the same telescope. All right? And that's indeed what people think was the problem. It turns out that in 1949, they had changed the cast iron cells that held one of the refracting lenses, and they changed the photographic emulsion they were using. And a few years later, 57, they made a lens adjustment that they only do very carefully. They try to put in corrections for all these things, but clearly the corrections were not enough. The fact that another star was behaving the same way as Barnard's star meant that the whole thing was not real. And unfortunately, people have still been looking around Barnard's star ever since because it's still close by. It still should have a big wobble. And so folks like Phil Ianna, who have been using the fine guidance sensor of the Hubble Space Telescope to do astrometry on Barnard's star, and they found that whenever Barnard's star seems to wobble, it means there's a problem with Hubble. It's kind of sad, but when they take out things that they found out went wrong with Hubble, that often they're the ones first to point out, because fine guidance sensors are used to point Hubble. So if there's a problem with pointing Hubble, you'll see it in this very high precision astrometry data. And when you take out those corrections for what Hubble is doing, there's yet no evidence for a planet around Barnard's star. But it's still close by. Maybe there's something there. We just haven't found it yet. Okay, so that's sort of the sad history of the method known as astrometry, where you're looking for the sideways wobble on the sky. But luckily, that wobble can also be detected through velocity measurements. In the same way that as a star goes around the center of mass, that means the light being received by an earthbound telescope is being Doppler shifted periodically. In the case of Jupiter, when the sun is moving, if you're looking at the sun from another star, at one point in time, the sun is moving away from you at about 30 miles per hour. 6 years later, it's moving at you at 30 miles per hour, and 3 years later, it's moving transverse to you. It has no Doppler shift at all. So if you could follow the light coming from the sun for a 12-year period, you'd see it Doppler shift back and forth by plus or minus 30 miles per hour, which was just about 13 meters per second. Now, if you've ever been driving through a traffic zone where a traffic cop's got a radar gun and you're going 30 miles an hour over the limit, you can imagine you're going to get a ticket. And so you say, what's 30 miles an hour? That should be easy to detect. But the problem is that if you're trying to detect this Doppler wobble, you have to compare that 30 miles per hour or that 13 meters per second with the speed of light. So you've got to divide that velocity by the speed of light. And when you do that, the fractional change in wavelength, which is what you get from the velocity compared to the speed of light, is about a few parts in 10 to the 8th. So you've got to measure the position of a stellar line to a few parts in 100 million, which is pretty tough to do. But it can be done if you have at least a bright star and a really stable spectrograph. The folks that first managed to strike pay dirt with this Doppler method are these two fellows here. Didier Queloz on the left and Michel Mayor. Michel is now retired. Didier Queloz just a couple months ago took over a major professorship at Cambridge University, starting up his own group there, independent of Michel's group at the University of Geneva. Mayor had begun a search for companions to single stars, which was published in the early 90s, and he found a lot of binary stars. He's sort of using Doppler to do what Van de Kamp was doing, was looking for binaries. He was finding them by Doppler. And he had 200 stars left over that he could not see any appreciable Doppler wobble. So he thought, these look like solar-like stars. They're solar-type stars. They seem not to have a companion, so maybe they are single stars. They would be good analogs for our own solar system. So in 1994, he built a new spectrometer on the Haut-Provence Observatory, a rather modest 2-meter telescope in southern France. And he got it working, and it had a precision anomaly of about 13 meters per second, which is just the wobble of a Jupiter. So he thought, hey, let's not only look for binaries, let's see if we can find some planets. And by the end of '94, they actually had some wobbles that looked pretty enticing. But by that time, the star was getting so close to the sun, they couldn't follow it anymore. They had to wait another 6 months for the star to come up in the night sky, and didn't come up again until the summer of 1995. And when they got the star up above the night sky again, they hammered away at that star about 8 nights in a row. And what they found was the following. A wobble, a really big wobble, of about plus or minus 55 meters per second, which is pretty large compared to their error bars of a few 10 meters per second or so, plus or minus. And this one here, I think they had just too much wine to drink that night, as far as I can tell. Europeans do have this tradition of drinking wine with their meals at the observatories. The Americans, the mountains are dry, unfortunately, to my great regret. That's a good argument for remote observing, actually, I suppose, but keep that quiet. So anyway, this is a nice wobble. Clearly looks like it's real. And if you fit that curve, it's a nice sinusoid implying this planet is on a circular orbit. That sounds okay, much like our own, most of our planets. And the amplitude is large enough that it's about a half Jupiter mass object. That sounds good too. Everything sounds like what you might expect. The only weird thing was this orbital period was not 12 years. It was a little over 4 days.
Is any of that data repeated?
Excuse me?
Is any of that data repeated?
I don't think so. Well, yes, so it's 0 to 1. So yes. From 0 to 1 is unique, but this part here should be over here, yeah. They do play the same game. So this stuff here going up here is the same as this.
Was repeated.
I guess it's sort of right the yeah.
I was looking at the 1 at 0 and the 1 at 1.
I'm not sure. I have to sit and study it, but I think there's some repetition though. Well, it's not clear. Maybe not, because with a 4-day period, you can, and they had an 8-day observing run. Those might all be unique points. Okay, but the key thing was that other folks, and the nice thing was this was confirmed shortly thereafter, which I'll show you in a moment. But the key thing was the Swiss were prepared to look for a short period planet, because Michel Mayor had been in this business looking for binary stars, which can have very short period orbits. They can have orbits of days or hours for the really close contact binaries. So he was used to sifting through his data trying to find even short period variations. Whereas the folks who were doing the Doppler planet searches, who you'll see some in a moment, they had this mindset, well, gee, Jupiter has a 12-year orbital period. We better take data for 12 years before we even start reducing our data to look for a planet. I went to a conference in 1993 where folks have been taking data for 6 years, and the Doppler planet search folks were in the audience, and some august person asked them, so what have you guys found so far? Any wobbles? And they said, well, we've only been taking data for 6 years. We haven't gotten around to reducing the data yet. All they needed was 4 nights of data to find this. Mayor was mentally prepared to look for something that other folks were not looking for, and he found something. And the great thing was with a 4-day orbital period, it only took 4 more nights for someone to confirm it, unlike the Barnard star thing, of course, which took 10 years to be disproved. But they made the announcement, Mayor made this announcement at a meeting in Italy. Within the next week, Jeff Marcy and Paul Butler is a colleague of mine now, were able to reproduce it with their own telescope. You can see this really horrible slide that I used to make the PowerPoint image. This was kind of these folks were not well funded back then. When I asked Jeff Marcy, can you send me a slide like I use in my talks, that's what he sent me. It's kind of a crappy slide. But to my mind, it's kind of like having a Babe Ruth rookie card. You know, you don't want to lose that because that came from Jeff Marcy before he was Jeff Marcy. You know, it's kind of neat. So I like to put that in the talk just to let you know that not every astronomer is always well funded at everything they do. All right, so clearly this thing was real. Beautiful tight correlation, 4.23 days. And just to show you what Jeff Marcy and Paul Butler looked like when they were young men, here they are in the dome of the Shane telescope on Lick Observatory. That was back before Jeff's hair turned gray and back when Paul still had hair. Don't tell him I said that. Okay, so the Doppler folks have gone on to great and glorious things, and in particular they found not only things like these hot Jupiters, this Jupiter mass object orbiting in a short period, which means it's very hot, so close to its star, but they pushed their Doppler precision down from 10 meters per second down to 1 meter per second or even less. Along the way, they've shown that there are a number of objects which are probably better classed as rocky planets rather than rather than gas giants. So here is an artist's conception of which this was an astronomical image. What's a system of at least 3 super-Earth mass planets, masses of maybe 5, 10, 15 Earth masses around a star called HD 40307. They are cleverly named B, C, and D. To this day, you're not allowed to name a planet other than B, C, D, E, and so on. We occasionally still argue about that, but astronomers are still happy with that. That seems to suit them fine, rather than giving them colorful names like we do for asteroids. And the key thing is that these super-Earths might actually be analogs to rocky Earth-like planets. If you go to this discovery space plot, they fall down here. So what I'm showing you here is the mass of the object is determined by the Doppler, which is actually only a lower limit because there is an ambiguity of the orbital inclination. So these are, sort of think of these dots as possibly a little bit higher. And this is in units where here's 1 Jupiter mass, 10 Jupiter masses, 1/10 of a Jupiter mass. Earth is right down off the scale here because it's about 300 times less massive than Jupiter. And in this direction we have distance from the star. These are mostly solar type stars, so that's an appropriate scale. And so here's 1 AU, 1 times the Earth-Sun distance. Jupiter's out at 5.2, Saturn around 10. The key thing is these guys are all in the range of being gas giant masses or even super Jupiters. 1 to 10 Jupiter masses. If you get much higher than about 13 Jupiter masses, you're not massive enough to burn deuterium. So or do any fusion whatsoever. If you're below 13 Jupiter masses, above that you can actually burn deuterium for about 1 million years or so during your early lifetime. Then you burn up your deuterium, then you become a brown dwarf. But below that, you are allowed to be called a planet because you never undergo any hydrogen fusion of any sort of the type that we use to define what a star is. So these are planets with the solid dots. So the key thing is here are these hot and warm super-Earths that began to be found. And there's a bias due to the Doppler detection method. You tend to find things on short period orbits because that makes the largest Keplerian velocity. And at any one time, if you've only been following things for 1 orbital period, you can't go too far out to long period orbits because you just haven't been following them long enough. So there's sort of a curtain drawn here and here saying that there may be lots of objects here, but we're not going to find them until we observe longer or improve our precision. So here they've improved the Doppler precision. There should be another dashed line down here showing they can now find things in this box here. The question is, are these merely ice giants that migrated in? Because we think the hot Jupiters, for example, theorists cannot imagine making a massive Jupiter object very close to the star where things are much too hot to be able to accrete any very much rock, much less ice and gas. We think the hot Jupiters formed out here somehow migrated inwards, probably interacting through the disk somehow. Maybe these guys are just ice giants that migrated in. Maybe they're not really Earths. Maybe they should be called super Neptunes. Well, one of the arguments against that is that in a number of these cases, people have followed the system long enough to realize these hot super-Earths have outer gas giants. Mu Era, for example, has 3 outer gas giants. Let's see, the blue one, 55 Cancri, has 3 also. GL 876 has at least 2. So this is beginning to look like sort of the structure of our solar system. Inner rocky bodies, intermediate gas giants, and then maybe some ice giants out there that we cannot see yet. If you tried to imagine these to be ice giants that somehow migrated in, they would have had to go past these guys first. And that's very hard to imagine. And even the most creative theorist, I don't think, has come up with a good way for having that happen. So more likely, these things formed as a system, and they perhaps all migrated in a little bit. And so this really is a good case can be made just on that ground alone from the architecture of the system that those are probably rocky bodies, the top end of the spectrum that presumably is that of rocky planets. And in fact, the RV folks, even before Kepler was launched, which you'll see in a moment, had estimated, based on Mayor's radial velocity surveys, that roughly 30% of solar-type stars have these relatively short-period super-Earths, which is amazing. Remember, in 1995 we had nothing. 2009 we have, 1/3 of the stars have these oddballs. Not that we want them particularly, but hey, they're better than nothing. You know, they're not exactly, we have no analog to these in our solar system. It would be like having a planet inside Mercury's orbit, which was 5 times the mass of the Earth. That's not our solar system, but it's a pretty good start. It shows at least a lot of stars have something out there. All right, what about another technique altogether for finding planets? There's another technique called transits. Namely, if you have a hot Jupiter just by random orientation of the orbits, roughly 10% of the time, that Jupiter should pass in front of its star, and you would see the star's light blink by a little bit during the hour or so, few hours that the star is being transited by the planet. In case of a Jupiter around the sun, Jupiter is basically 10 times smaller, so its area is 100 times smaller. That means a solar-type star will dip by 1%. That's actually a change in luminosity of the star that can be measured from the ground, from the Earth. And we actually had found 10 hot Jupiters before any were found to transit. And people were getting a little bit anxious because they said, the chances are 10% that these will transit. We found 10. How come none of them are transiting? People start worrying, well, maybe they're not really planets after all. But when the 10th one came along, HD 294558b, by golly, it transited. Thank goodness. We had to wait till the 11th one. There probably would have been a tremendous loss of faith. So here's the first transiting planet. This is sort of the 1%, a little bit more like a 2% dip in this case, because it's a little bit of an inflated planet. Discovered by David Charbonneau and Tim Brown. They discovered this with a 4-inch telescope in the parking lot in Boulder, Colorado. Amateurs can do this, and they're professionals, but they knew that they'd had a prediction that from the radial velocity, the Doppler measurements, they knew when to look, and they got clouded out towards the end of this night, so there were two nights they looked at it. They couldn't quite get the rest of this one, but that's a pretty clear dip, and that's also pretty good. So that can be done. And in fact, HD 294558b is still one of the real poster childs for hot transiting Jupiters. And again, I wish we had a real astronomical Hubble image of this, but here's an artist's conception. It's actually in the process of losing gas. It's so hot that it actually gives off what's called Lyman alpha emission associated with very hot hydrogen atoms, which is given off in the ultraviolet, which is sort of blue. So the artist was being a little bit accurate here by making it look like it has a blue cloud. It's really an invisible to our eye ultraviolet cloud, but what the heck. We'll give them that little bit of, this does give you a feeling for if you could be there in person, not that you would want to be that close to this thing. You're talking about being at about 6 times closer than Mercury is to our star. It would be a very hot region, but it would be a spectacular sight to see. Okay. Now, what about other ways of finding planets? Again, indirectly, as transiting is. And so I think roughly 100 or so planets have been found to transit by ground-based searches. There's also something called gravitational microlensing. This is something that Einstein had predicted back in 1936. He didn't even want to bother publishing it, but a fellow in Eastern Europe kept hectoring him about it until finally he agreed to publish it just to get the guy off of his back. He figured it would never be detected, but he predicted it should be an effect that would be possible. He just figured it would be coincidental if you could ever get this to work. The basic idea is if you look at a background star and the light's coming out equally in all directions, and if a foreground star happens to pass exactly along your line of sight to that background star, then the gravity of that foreground star will bend some of the light from the background star in your direction. Otherwise, it would have gone past you. Instead, it comes towards you. And since you're getting extra light, you think that background star is getting brighter. You never see the foreground star. You don't even know it's there, except you're looking at a background star, and suddenly it brightens for maybe a month or so, and then dims again. Very strange. If there's no other reason, if it never does that again, you say, why did it do that? Well, the only interpretation that people come up with is it has been passed by a foreground star. And if in addition, on top of that month-long brightening, you see a short one-day spike, that means there's probably another object in the system. If it's correctly placed at just the right angle to do the light bending called the Einstein radius, appropriately enough, then it will get that secondary brightening for a much shorter period of time. So when you see those month-long events with a short period brightening, if you do some very sophisticated model fitting to it, you can say, hey, we can find a planet that way as well. And the first microlensing detection dates back to also fairly recently, 2004. That's the star that was being followed. This is not the star that has a planet around. This is the background star that got brighter because its light was being amplified and then faded again. Not very spectacular. So again, we go to an artist's rendition of what it might look like if you were there. This is done with a rather modest telescope at Las Campanas, Carnegie's observatory, run by a Polish team. 1.3 meter telescope. It is there Every time the galactic center is up in the South Pole region, the Magellanic Clouds, they're out there every night taking data, finding literally hundreds of more transit events that can be followed up to see if they have planets. Okay, the microlensing folks only have a little over a dozen or so detections, but the nice thing about them is they fill out a different region of discovery space. You know, the Doppler stuff tends to be in close. They're out at sort of the Einstein radius, which is roughly the asteroid belt around a solar-type star, and so they find these things out here, and they find not only these big moosey Jupiters, which are kind of cold because they're far out, but they also find super-Earths down to Earth mass or below. And these guys are kind of hard to find. They do not amplify quite as much as a Jupiter does, so the fact that they found a fair number of these means there must be a lot of these Earth-sized planets as well as the Jupiters around their nearby stars. And the folks that actually do the statistics on this, they've only got, like I say, a dozen or so objects, but they are willing to predict that that means that given that they're most sensitive to fairly massive planets, but they do find some small ones, that when they do the numbers, these super-Earths are maybe around 60% of their stars. You know, we were at 30% with Doppler in close. These guys are sampling a little bit farther out. Now we're up to 60%. If you add the two, you're up at 90%. We're getting somewhere, you know? Getting close to what Terry was saying at the very beginning as a teaser. Here's the reason why this supports those statements. If you go to a bit more massive, it drops down a little bit, which is again kind of odd because that means that these terrestrial things are perhaps even more common than the easy to find gas giants. Gas giants are there as well, but the ones we're most interested in for having life are down here, unless you want to talk about a moon to one of these Jupiters, which might not be a bad place to look for life, but we really hope to eventually find something like an Earth analog. So that's pretty promising too. Even more recently, the microlensing folks have seen some events where they didn't see that month-long brightening due to the foreground star. They just saw the short one-day brightening due to apparently a planet with no star nearby. And from that, they really went wild. They had only 3 of those events. But if you believe in 3 events, they claim that actually that was explainable by having Jupiter mass objects, which is this 10 to the minus 3 of a solar mass. That's Jupiter mass. They claim that for every main sequence star in the galaxy, there must be 2 of these free-floating Jupiter mass objects. So if you have 100 billion stars in the galaxy, depending on how you count brown dwarfs and M dwarfs and stuff, that means you've got 2 billion free-floating Jupiters. That's pretty wild. I'm not sure if I'd go along with that. That's even radical for me. My feeling is that they're probably out there, but they're just far enough away from their host star that you saw the brightening due to the planet, but the star was not aligned so that it did a brightening as well. So you've got just the planet at the right distance, the right location for the background star, but not the star. But the star is still there that the planet is orbiting. You just missed the star. And there's some support for that idea because folks have been able to start finding distant planets. Here's the most spectacular case to date, a system, a fairly massive star, 1.5 solar masses around a star called HR 8799. This is work done by a Canadian group using the Subaru telescope with some very clever adaptive optics, where they're trying to get around this contrast problem by blurring out the central star. So what you see here, these speckles, are the leftover light that they couldn't quite cancel out. They did their best, but if they did not cancel out that light, you wouldn't see anything at all out here. You see a huge booming pattern from the bright star. But by canceling it as best they could, they picked up B, C, and D. And this is the first discovery image when they only had 3. They since went back and found, I think, this speckle here. As they took more and more observations, it didn't change. Speckles will come and go, but that thing was always there and is even orbiting a little bit. That means that one is real. That's a 4th planet. So they actually found 4 planets out there at rather large distances. If these things were seen by the microlensing folks, beyond 10 AU, they might be able to find one of these planets, but they wouldn't see the wobble due to the star or the magnification due to the star. So I think that's perhaps the best interpretation of what the microlensing folks say, is that there are planets not so much free-floating, but they're just out there at great distances as well. Doppler tells us they're close-in planets. Microlensing tells us there are planets out at great distances as well, as does this search. Okay, so let me sort of summarize where we are right now. Discovery space plot again one more time, only now at Earth masses. Here's the Holy Grail. We're trying to find objects, maybe super Earth mass, up to 10 Earth masses, at the right distance to have liquid water, because we believe that really is a prerequisite for anything that's similar at all to Earth-based life. And we see a lot of these hot Jupiters. We have some cold super Earths, just about right super Earths, but nothing that quite fits within that magic band yet. So the goal is, let's find something which fits in here. And if you want to find them by transit photometry, which is a way of finding these things, you really want to go above the Earth's atmosphere to do detection. And while the NASA Kepler mission was launched a little over about 4 years or so ago, the Europeans actually beat us to space. The combination of the French Space Agency along with the other European partners launched the Corot space mission 3 years ahead of Kepler, trying to steal some thunder. It's a rather smaller telescope compared to Kepler. It's a 27 centimeter diameter telescope versus Kepler's primary is 1.5 meters with a 95 centimeter secondary. But it's a pretty neat telescope, and it has found some exciting planets, the most important of which is called Corot 7b. And here's what happens when the planet goes in front of the star and makes the star dim by, as you can see, 4 parts in 10,000. That's, again, a pretty accurate measurement. There are some big error bars there, but if you take enough observations, you can believe that really is the dip to the planet. And in this case, it was kind of hard to do the Doppler follow-up to see if they could get the wobble, because the transit photometry just gives you the size of the planet. You only know how much of the starlight's been blocked out. So you have a size. If you know the size of the star, and then you know the size of the planet, but you don't know the mass, what you want to do then is go back afterwards with a ground-based telescope and try to do a Doppler measurement on it. The host star for Corot 7 is sort of a noisy K star. It's not one you would normally pick to do Doppler on, but they hammered away at it and they came up with what they think their best estimate is. And it turns out to be something like 5 Earth masses with a density. You can now get a density, right? You've got a size and a mass for the first time. You can see, are these things really what we think they are? Are they snowballs? Are they uranium pellets? What are they? Well, it comes out to be 5.6. Earth is 5.5. Of course, it's much more massive, so it's probably in some sense intrinsically less dense material, but it's just been crushed more because it's more massive. But that's a pretty close fit to the Earth. So at the time, that was the most Earth-like planet in terms of its gross properties that was known. Okay, but NASA did get out of the starting blocks and 4 years ago launched the Kepler mission, which I affectionately refer to as TPFT. NASA, and I in particular, have been working for 20 years to define the parameters for a possible terrestrial planet finder space telescope. I'll show you some of the designs in a moment, but none of them have come to fruition. So instead of having a TPF interferometer, TPFI, or TPF chronograph, TPFC, we have TPFT for transits, which no one really thought was going to get funded. This came out of actually the Planetary Science Division of NASA through something called the Discovery Program. The PI, Bill Barucki, he worked on this thing for 20 years trying to convince people it could be done, and he got it to fly, and it's performing spectacularly. The whole purpose of it is to try to figure out statistically how often Earth-like planets occur. You get a sense of the difficulty by seeing this NASA graphic. It's even more clearly focused in this image of a recent transit of the Sun by Venus. Venus is essentially the same size as the Earth. And the key thing is, this gives you a sense for what something is like when it's 100 times smaller. That means the amount of area of the star you're blocking is that factor squared. So you're blocking 1/10,000th of the starlight. You've got to be able to measure a star dimming by a part in 10,000. There's no way you can do that from below the Earth's atmosphere. Put in the most adaptive optics you want. The Earth's atmosphere, even on our highest mountain peaks, will not allow you to do that sort of photometric precision. That's why you have to go to space. That's why Corot was launched in part, and especially why Kepler was launched. It's a difficult thing to do. But the Kepler team was able to prove in the laboratory ahead of time that they could measure with genuine charge-coupled devices, the same sort of devices that make your digital cameras possible. They could measure changes in luminosity by a part in 10 to the 5. They only need 10 to the 4th to see the Earth, so they showed they could have the signal to noise you would need to find an Earth and prove it was there, Or if stars don't oscillate, you can prove that they're not there too, at least not transiting. Okay, so Kepler was launched almost 4 years ago. It stares continuously at a field just a bit off the galactic plane where stellar density is very high. We want to be close to the galactic plane but not right on it, because if you get too close to it, the stellar density is too dense. You can't see individual stars. You don't want to be too far away from the galactic plane, because then you don't have very many stars in your tiling of, I think there are 48 detectors here altogether, of which essentially 22 of them have been functioning perfectly fine throughout the mission. It's roughly 10 degrees on a side, so it's like 20 moons in each direction. That's the size of the field of view. It's close to the Cygnus and Lyra constellations, and some of the brighter stars actually fall within the Kepler field of view, but they very carefully, as you can see this bright star here, is placed near the border between two CCDs, because you don't really want a bright star on your CCD to saturate the image. So they very carefully, they went through probably a year of study to find exactly this right field and orient it just this angle, and if we can hold it there and not move it, we'll have the best possible precision. Because Kepler basically stares for 3 months at a time before it has to do a little bit of a roll to make sure this got its solar wings pointed towards the sun the right way. And it stares for 3 months at a time. It can never close its eyes. It had a dust cover that was blown off, sort of one of those tense moments after a launch. If the dust cover doesn't come off, we've got a telescope in space that can never open up its eyes. The dust cover was blown off. But for those of you who are really old, just to date myself, have you ever seen the movie Clockwork Orange? There's this phase where Alex has got his eyes forced open. He's forced to watch these violent movies. That's kind of what Kepler is doing, only he's doing something very positive here. It's staring continuously, because you want to look at these 150,000 odd stars and wait for one of them to blink, and wait a year later and see if it blinks again, and wait a year later and see if it blinks again, because you want to see multiple blinks to see if they're real. You need at least 2 blinks to get an orbital period, and you want to see a third one to make sure that it wasn't some anomaly. And if you really are having problems with the noise, you want to see as many of them as you can to add them up together and use the statistics to make sure you really are detecting something real. And in fact, one of the problems we had with the mission was that we were basing our estimates on how noisy stars are on the sun. We have a lot of information about how the sun's brightness changes, because of course it's the easiest star to measure. We've had spacecraft measuring the stellar luminosity, and it's actually a pretty quiet star. We figured, well, that's probably a typical star. Turns out that most G-dwarf stars like the sun are about twice as noisy as the sun is. That's bad. That means when you're trying to find a very tiny part in 10 to the 4 dip, stars like the sun have dips like that twice as often as the sun does. And so because of that, the Kepler folks, and you didn't know that, of course, because Kepler is doing something unheralded. They are returning information on the brightnesses of stars equivalent to what we know about our sun. They're doing it for hundreds of thousands of stars for the first time ever. And so Kepler has, besides its planet finding stuff, has revolutionized the field of stellar seismology, folks who study how stars oscillate. Those folks are getting as many, if not more, papers out of Kepler than the planet hunters are, because it's completely changed their field. Anyone who studies stars for a living, they want to use Kepler data if they haven't already. Even the Crow just failed this in November. Their computer died, and so even the Crow people, who used to keep their data all to themselves because they were proprietary, they're, believe it or not, all coming over. Say, you got any Kepler data I can look at? Because that's now the big game in town. Okay, so because of that Kepler, we'd hoped to get the final Kepler results out right around now, 2013, but because stars are noisier, we need to run the mission for about twice as long. So maybe another 3 or 4 years before we really have a really solid number for what the frequency is of Earth-like planets, but Kepler is on its way to doing that. Okay, just to give you some of the highlights from Kepler, here's its first rocky planet, cleverly called Kepler 10b. And this one, again, artist's conception. This one is, again, about 5 Earth masses. This is one where they are able to find a Doppler wow because it's on a short period orbit, less than a day. This guy's really in close, really hot. This one comes out to be 8.8 grams per cubic centimeter. And that's actually more accurate in some sense than the Crow 7b one you saw earlier, because if you put that on a plot of radius versus the mass, here's Crow 7b, where they weren't really quite sure the Doppler velocity was not very accurate because of its noisy host star. For Kepler 10b, the star is more well behaved, so they got a good Doppler mass. so they knew pretty much what this mass was. And the photometry is better on Kepler too, because it's a bigger space telescope, better CCDs. So they really nailed that Kepler is right there, whereas Creux 7b could be anywhere in this box. And here are the curves for where you would be if you were made out of pure iron, an Earth composition, or a water planet, sort of like a Neptune or Uranus that came in and melted. So Kepler b is clearly right here at Earth, or maybe a little bit more like a Mercury, which has a lot of iron. Creux 7b, that might very well be Earth-like too, but it could also be more of a water world. So that makes the point that the Kepler 10b really is sort of holds the record for the best characterized Earth composition, to the extent that one number, the density, can tell you what Earth composition is. We like to know a lot of other things about it, but for the moment, that's all we've got. Okay, so Kepler has been running for 3.5, almost 4 years now. They begin to announce the data every year or so. Here's the first data release, June 2010. They only had basically 60 days worth of data, so there's nothing here with an orbital period much more than that, just a few where they had seen a single transit and inferred from the transit duration what the orbital period was. They had found 312 planets by then. The ground-based transit folks had found a total of 100 with 10 years of work. Kepler found triple that number in 3 months. Well, a little bit less than 1 year later, next data release, 1,235 is the body count. You can see there with the newer plots, they're going out to longer periods, as they should. So they get more and more greater time span, and getting down to lower mass, or I'm inferring lower mass, it's really lower size. Here's Earth size, Neptune size, Jupiter size. Again, we do not get masses directly from Kepler. You have to do Doppler follow-up if you can. But it's kind of hard to do because a lot of the Kepler stars they're all off towards this constellation, which they're unfortunately pretty faint. They're not nearby stars. 1235, all right, that's second data release. Here's the third data release, December 2011. 2326, well, you're starting to get some return on your investment here, by golly. Your $600 million has been well spent. If you divide that, $1 million per star or so, you're down to a few $100,000 per star. Okay, again, yellow points are going farther and farther down, a little bit farther out in orbital period. And then the one that just came out a couple of weeks ago at the Long Beach AAS meeting, here we go, 2740, and more to come. Remember, we're now roughly halfway through the mission, because NASA has agreed to extend the mission because of this problem with the noisiness of stars. So we're just going to keep going. And the amazing thing is, these guys up here are the easiest to find. The observational biases are such that if you're a longer orbital period, it's hard to find those because you want to see multiple transits. If you get too small, the transit dip in luminosity is so small you can't tell from the normal oscillations in the stellar luminosity. So there could be lots more down here you don't see. Up here, you're pretty complete. And the main thing is, my God, it just looks like there are an incredible number of these super-Earths, for want of a... I mean, these are in short period, so that, subject to that same argument, these probably are mostly rocky bodies. They're sort of in the range of perhaps 1 to 15 Earth masses, if these densities are correct. There are a lot of these bodies at those distances. And the Kepler folks are pretty careful not to go ahead and give you estimates of what the frequencies are. But here's just a feeling for what they found so far with the most recent data release. These are, again, easiest to find, the big ones, and there are a lot of Jupiters out there, but not too many. But they really start finding more and more of these super-Earth size. And then at this point, they're seeing smaller and smaller numbers because these are the hard ones to find. This is where you're incomplete. So if you could really have an absolutely precise mission, presumably this function would continue rising up here. And the Kepler folks are being very careful. They don't tell you, well, there's 50% have Earths or 35% have super-Earths, because they don't want to say the answer yet. They want to do the whole extended mission and give you a real number at some point. In the meantime, other folks go ahead and get the Kepler data and make some wild extrapolations. So one group took some of the early data releases and said, well, this means that 2% of solar-type stars have Earths. Another group, also at JPL, took the same data and says, oh, this means that 95% of stars have Earth. So you can see there's still a little bit of a slop when you do an extrapolation. That's why the Kepler team keeps their mouth shut. It's folks outside the team that will go ahead and say whatever they want to say, but Kepler is going to try to get it right. Of course, the whole point of Kepler is to find habitable planets, not just planets in general. So they're trying to find objects out with 1 year orbital periods. They've only been taking data that was published for basically 3 years, so you really want to see multiple transits, as I saw. So just beginning to find planets out in this region here, which is colder temperatures, meaning farther away from the star, meaning orbital period. So again, they find these guys easier, but these guys will take them more time to find them. And right now they have, what, 58 planets, some of them fairly massive. But a Jupiter up there, might have a habitable moon. So they sort of count not quite orbital planets, but orbital, habitable, not habitable planets, but habitable moons. And exactly where you call the habitable zone depends on lots of messy factors, like how much of an atmosphere you have. So this is kind of exactly where you draw the boundary for having liquid water can depend on other parameters put in the problem. But they already are showing that they do have a number of objects down to Earth size, and give them another 3 years, they will go down below this limit. And you'll see up here, these are easiest to find. There's a bit of a pile up down here. This is where you're observationally best able to find them, telling you that if you could keep doing the mission, you should find even more down around here, which is where we really want to be. So that's pretty exciting. Of course, there are some hints that we already have habitable planets from the RV folks. This is system Gliese 581, looking around an M dwarf where the habitable zone is in closer because an M dwarf is lower luminosity, like Barnard's star, than the sun. And there are some claims, including those by my colleague Paul Butler and Steve Vogt from Lick Observatory, that this system here of 5 Doppler planets, C and D are sort of on opposite sides of the habitable zone. The claim is maybe there's a 5th planet G in here. Actually, I lost count. There are 6 here altogether. They found G was the 6th one. If this planet is real, where there's some debate about it, then that one is right smack dab in the middle of the habitable zone. That might very well be the first habitable planet. Even though it's around an M dwarf, that's okay. That's not a bad place to own real estate either. Now, what has NASA been planning on doing? I sort of hinted at the 20-odd years of planning. NASA spent $600 million developing this concept, the Space Interferometry Mission. It's able to do the old classical technique, looking for the wobble on the sky, and to measure that wobble to 1 microarc second, even better. This mission, if it was flown, could find Earth mass objects at Earth-like distances around 100 or so of the closest stars. NASA spent $600 million developing the technology of it, then they pulled the plug on it. Problem was James Webb Space Telescope needed the money. SIM did not get it. Bit of a problem there. But someday we're going to want to fly something like that because we're always going to want to get the masses of these things. And if it's unclear if ground-based Doppler will ever be able to find an Earth mass signature around a solar twin, it could be we'll have to eventually fly something like this to actually get masses, not just radii. But we not only want masses, of course, that's just a start for talking about the origin of life elsewhere. We also want to look for the ingredients of life. We want to read what's on this list over here. Protein, fat, carbohydrates, flour. What's the ingredients for putting it together? Heat circulate for 1 million years. We want to look for the atmospheric molecules that might be indicative of either the habitability of the planet. Basically, we want to be able to find water for sure. Carbon dioxide is very common for terrestrial planets, Earth, Mars, Venus. And in addition, so those are sort of what you need to get going, but if you can also find something like methane or ozone or oxygen. Oxygen is thought to have been produced primarily by cyanobacteria over the last couple billion years. And methane is produced also by not cyanobacteria, but by methanogenic bacteria as well as dairy farms. So perhaps we can get the American dairy industry to help us look for methane on other planets. But in order to do that, we need to be able to separate out the planet's light from the starlight. Be able to get back to that direct imaging problem. We want to see the planet out there away from the star and measure its spectrum. NASA's plan to do that. Here's one of the terrestrial planet finder concepts, a coronagraph. NASA also spent $100 million or so developing these designs. They're not quite as advanced as SIM was, but they basically figured out that what was known at the time, that if you flew a 3.5 meter by 8 meter optical telescope with a coronagraph, which is basically a sophisticated way of putting your thumb in front of the star and seeing what's off to the side of it, that would be able to image Earth's around, again, 100 or so nearby stars. Unfortunately, this one cost about $6 billion minimum. That did not go very far either. Infrared wavelength, as you saw earlier on, you only need 1,000,000 to 1 contrast, but because your infrared wavelengths, you've got to be a lot bigger. Instead of having an 8-meter diameter, you better have an 80-meter diameter. Don't want to assemble that in space, so you have an interferometer. You have a little fleet of, say, 4 1.5-meter telescope, link them together, combine the beams using interferometry, so it's effectively the same aperture as an 80-meter beam. That will do the same deal. 10 times longer wavelength, 10 times larger spacecraft. And the Europeans would be willing to partner with us on this. They also have a very active group who love to build a terrestrial planet finder. Their concept, they came up with something called Emma Darwin. Emma was the wife of Charles Darwin, appropriate name. And they came up with, well, here's what they thought was the best, for technical reasons, best array. They called the X-array. And the NASA JPL folks got together with the Europeans and said, you're right, this is the best design. So there was actually a concurrence between NASA and ESA. Let's build this one together. Again, unfortunately, price tag of $7-8 billion or so. No more than what JWST costs you now, mind you, but we didn't know that at the time. So TPF is also kind of dead. In fact, right now, the only game in town is this one. The National Reconnaissance Office built a couple, 3 assemblies, 3 primaries and 2 complete assemblies of 2.4-meter space telescopes to be used to point at the Earth, oddly enough. They decided not to use them. They've been sitting in cold storage up in upstate New York for 10-odd years. And a year or so ago, they decided to donate them to NASA. And Charlie Bolden's taken it seriously. There are two of them that are being analyzed right now. One of them is being analyzed specifically to meet the highest priority of the last US decadal survey, which is a dark energy mission combined with microlensing, obviously enough. So that's been sort of sequestered off, if I may use a favorite phrase in Washington these days. The first one would be used for doing the W-FIRST mission, as it's called. But there's a complete second array, and there is a competition going on in Huntsville, Alabama in 2 weeks where other uses for the second telescope will be considered. And one of them is it's a Hubble-sized telescope, much faster optics though. You can see it's much more compact than Hubble. Here's the primary and the secondary up here, with a very wide field. It turns out that this would make a wonderful planet-finding telescope. It would be basically, if you could redo Hubble and engineer it particularly just to do planets, it could do wonderful work on being an internal chronograph. It can do astrometry. If you put little spots on the primary mirror to give you as reference points instead of the background stars. And it could have a spectrograph that can measure spectra, much like the current Hubble has done for some of the hot Jupiters. Here's some work by Mark Swain of one of the favorite transiting planets, HG 189733, showing you some observations using the old Hubble NICMOS instrument compared to a model spectrum, showing that they have detection of carbon monoxide, CO2, and water. This is showing that that planet, it's unfortunately a steam world. It's a hot Jupiter. But it shows the technique that you can indeed find spectral features that are indicative of 2 of the biomarkers that we want to look for in a habitable Earth. So that's where the field is hoping to be heading for. Maybe one of those NRO telescopes will be used to do something. But even that won't satisfy us, because we really want to know more than just simply a few spectras and a blurry spot of light. We really would like to get a picture sort of like that maybe. Wouldn't that be nice? That'd be great. This one here, even to get that one at visible wavelengths, you would need 2 17-meter diameter telescopes spaced 120 kilometers apart. I wouldn't want to price that one out. But this will keep us busy for a while, folks. So if you really want to look to the future, that's what we can perhaps hope for sometime in the distant future. So I hope I've given you tonight a good feeling for some of the history of the field, where we are right now, and some of what the future holds, which is mostly that NRO 2.4-meter telescope. And if you want to know more about the past of what's gone on up to the launch of Kepler, I will shamelessly admit that I've written a book about this recently called The Crowded Universe. It was published at the same time Kepler came up, so it's not anything that's happened since Kepler is not in the book. But if you want to know the history of the field up until 2009, that's one place to look. Thank you very much.
Okay, we have time for 2 very well-directed and brief questions.
And I will give you a lengthy answer.
Schedule. Any questions? So I have a question for you.
Okay.
What were the NRO telescopes originally designed for, or can't you tell us?
They were going to be using for satellite surveillance of the Earth. They're part of the KH-11 series, the Kennan space telescopes. It was unfortunately a rather large program which was canceled after they spent untold billions of dollars on it. It's a bit of a shame, but unfortunately the other agencies of the U.S. government are able to spend a lot of money on things which they are not taken to task for when they don't come up with something. But I will note that, oddly enough, 1 month before the NRO made this offer to NASA, I had happened to publish a letter to the editor of the Washington Post following up on a commentary I saw about, they talked about all of the weapon system that the Pentagon had developed that had gone nowhere, and they'd estimated $35 billion had been spent on developing weapon system in the last 10 years that eventually decided to cancel. And I wrote this sort of tongue-in-cheek Swiftian thing saying, gosh, if the Pentagon wants to protect us from alien invasion, we should be looking for life on nearby planets, and if you have some ideas there, NASA will be happy to tell you how to build such a space telescope because we know how to do it. And then 1 month later, the NRO released these telescopes to NASA. I have no idea if there's any correlation in reality, but I'd like to think that somehow that little letter to the editor in the Washington Post might have caught someone's eye. Who knows?
Quick question. What are the gravitational considerations of a 15 times Earth-mass planet for life?
You look like a rhino, kind of built low to the ground. Of course, the life we're really looking for in the first instance is not something as wonderful as we are. It would be microbes, and they don't particularly care about how strong the gravity is. That's really what we have the most hope of seeing, is something equivalent to our early Earth, where we perhaps have evidence for life going back close to 4 billion years back. That's something that people argue about, but we know for sure. We've only had multicellular creatures for the last 500 million years. So for the first 3.5 billion years, we had single-cell life, which should still be pretty exciting to see. If we can find a planet which has an atmosphere with both methane and oxygen or ozone, while they can be each produced abiotically, to see them in the same atmosphere must mean there's got to be a very active source of both of those molecules. And abiotically, it's very hard to do that, to have the chemistry work, because those two molecules will react with each other. So if you can find a planet with both swamp gas and ozone, that probably means there are some little tiny critters there that are having a happy time.
We can wait 1 billion years, we'll meet them.
Well, that's a whole other thing. Of course, if we actually find evidence for a nearby planet which has some sort of, not only is habitable, but perhaps is inhabited, we're going to think, wow, what's the next step? We're not going to send human beings there, but sending a small spacecraft and waiting 1,000 years for it to get there maybe and send a signal back, that's something to, to think about really. I mean, that gets into science fiction, of course, at that point, but we're getting close to where there's actually a 100-year starship concept that I think DARPA put some money into. They had a workshop this summer talking about how would we try to, if we wanted to work for 100 years, how do we go to a star? So people are actually putting some, not a lot, but some money into taking this seriously.
I wonder if you could comment on maybe the relative probability of finding life within the solar system on moons compared to the yield that you get from looking at the light far, far away.
That's a horse race right now. That's what we're doing on Mars. NASA doesn't like to say it, but Curiosity rover is really looking for life. But they don't want to they want to say more like we're following the water, or more, really they're following the methane in some sense, because we know that Mars has methane. The question is it abiotic, or is it due to fossil life, which is now decaying and issuing out? And I'd say that's I think it's a horse race. It's unclear if we'll find evidence for something on Mars, or I think Mars is the best bet right now, obviously, since there's a huge NASA planetary science budget is basically Mars focused right now, even though folks would also like to look out on Europa. But they could find something, Curiosity could have something within a year, or the next Mars sample return possibly, and lander they're proposing to launch in, I guess 2020 is the next date for it. That could find something. And who knows, if we could, by this time we thought we would have built a terrestrial planet finder. Those of us who have been planning it for 20 years thought we'd have the data already done. We would have thought we'd done it already. It's going to take us probably another 20 years to get one of those up if we can, unless one of these NRO telescopes somehow comes into being. So who knows, a lot of big uncertainties. If I had to bet, I would probably put my money on Mars, because we know that, we're on Mars, we're digging around there right now. I'd have to put my money there, even though I'm more an exoplanet type guy, but I also don't like to lose money on bets, so that's where I would bet.